You have to spend a lot of power, and therefore overall bad things about valves that they were occupying large side. They are consuming a lot of power, and not only power, the voltage requirement, the voltage levels were also usually in excess of 100 volts. So servicing an electronic circuit that time was not as easy as it is today. Getting shocks are very typical. People are very happy, very alert about it. And because of the large size and power consumption, it was not possible to have complicated electronic functions, to be implemented in a practicably small size, small power way. And that was the main problem. And as you know that during the Second World War, you know that all these things, many of these inventions came from the war requirements. Second World War, they found that the Second World War was predominated by, the flight, the bombing, all airplanes and all these things were there during Second World War, and heavy things were really something very difficult to be controlled during the Second World War. And of course by that time miniature valves came, something like printed circuits, not exactly the PCBs of today, were also there. They could integrate a number of valves in a small ceramic package, and all these things, innovative things were there, but still the size was big, and they found that it was too inconvenient. So the work people, they said that could you do something? For example, the first proposal, first proposal of this so-called integrated electronics or integrated circuits came from a physicist of Royal Radar Establishment, UK. His name is a very famous man. His name is Dummer, G.W.A. Dummer of RRE, Royal Radar Establishment of UK. In 1952, he told in a conference that you see that because by that time the transistor was discovered, 4748 transistor was discovered. Though the package transistor was big in size, the actual transistor, as some of you have already known, it is very small. It occupies usually an area of 0.5 millimeter by 0.5 chip. Transistor chip is usually of size 0.5 millimeter to or 1 millimeter by 1 millimeter. So he said that if a device can be made in such a small form, what is the problem of having millions of such devices in a three-dimensionally packaged form? That was what he thought that time. He said that yes, if electrons can do such nice functions like amplification, on-off, that means switching, then oscillation, sustained oscillation, spontaneous oscillation of electric current or voltage. So he thought that this particular aspect could be perhaps extended to a three-dimensional geometry. That means these small tiny devices could perhaps be one day packed in a three-dimensional form to perform complicated functions in a very simple way, as perhaps our human system is doing, because something about our brain was known by that time. They thought that yes, our brain is such a small thing, it can do such huge things. Anything it can do. Today, that as we gradually are knowing brain more and more, we are astonished. Power of nature or power of God, we are really astonished. And that was the proposal. But he was a physicist, but he gave the idea, And at that time, that as I said, that warmongers, it was picked up quickly, particularly the USA. USA that time was a superpower, only superpower, though USSR was coming. But USA was a superpower, there are a lot of money, natural gifts. So they started in the Air Force and Army, as well as to some extent Navy. They started thinking about it. In fact, there are huge investments from Air Force, Army and Navy of US government to the important companies like Texas Instruments, Fairchild Corporation, RCA, IBM and other leading companies that time who were producing complicated valve electronic systems including computers. And they invested a lot of money. As you know, the Bell, and another very important name of this, that is Bell Laboratories. You know that Bell Laboratories is the pioneer. But unfortunately, the first IC did not come from Bell Lab. It came a little bit later. Anyway, huge investments were made to these various private organizations in USA, and they thought that something perhaps is possible. Yes, it was possible, you know, that because transistor is made from germanium, that first transistor was made from germanium, they thought, can we not place a number of transistors side by side? And can we not also try to make some resistors, capacitors in a similar technique? Because after all, semiconductor is a partially conducting material. It can be, by shaping it, we can form various values of resistors. It is natural to get it. And therefore, they started thinking about it rigorously. But there was a problem, because germanium material was naturally inconvenient for achieving that goal towards integration of a number of components in a small chip. Okay? By that time, you know, it was well known that silicon is a very interesting material. Germanium technology somehow from transistor making point of view was convenient in the beginning, but there are certain problems in silicon. So there is technological realization of a transistor is concerned. And as you know that these people that were putting a lot of money and a lot of brain power from all over the world, and they were successful in developing a technology based on silicon that is known as planar technology. Silicon planar technology, okay? This silicon planar technology, the main important thing is that silicon is such a material that if you heat it in oxygen at a high temperature, say around above 1000 degrees centigrade, or hydrogen and water vapor mixed, then silicon readily gets oxidized to form a very high quality silicon dioxide layer. Silicon dioxide is popularly called fused silica or quartz. Quartz is in crystalline form, it is called quartz, and in non-crystalline amorphous form it is called fused silica. So very nice quality film of silicon dioxide could be very easily grown on silicon, as I already said, that if you have a silicon substrate, this is a silicon substrate, one can grow very easily a very high quality silicon dioxide layer on it, very high quality silicon dioxide, a very simple technique, using a very simple technique, and that is nothing but treating it in dry oxygen atmosphere or in an atmosphere which contains oxygen and water vapor, which is known as wet oxidation atmosphere. Okay? And this silicon dioxide, by that time, another technique was already developed by the printing technology people, and that is what is known as photolithography. Transferring a pattern from a photographic plate onto something. For example, a medium for printing, a printing block. So photolithography technique and the discovery of a material called photoresist. It was done by Kodak, Eastman Kodak Company of USA, and after their name, this particular material was called KPR, Kodak Photo. It was a very popular trade name that time, KPR, Kodak Photoresist. And so photoresist and the art of photolithography already was available, but in little bit crude form, because it was meant for the printers. They were not interested in microns. They were interested millimeters or maybe sub-millimeters, never microns or sub-microns of today. Only thing which was done by that time by the researchers in the various laboratories like Bell Labs, Texas Instruments, Fairchild, Motorola, RCA, and similar other companies, that how to, that improve the technique, art of photolithography to suit the fabrication of semiconductor devices and of course today's integrated circuits. Alright? And they are successful, and they found that this silicon dioxide film can be very easily patterned into a very fine superstructure simply using photolithography. That means one can create windows in silicon dioxide by removing some part of silicon dioxide, so between this line and this line. So this particular portion of silicon dioxide between this line and this line can be removed by an automatic technique known as photolithography and etching, of course. And subsequently we can introduce some impurity atoms like phosphorus or boron to form the so-called p-type or n-type layers, either P or N. That means to form p-n junction, and that is the main thing. You know that for transistor was discovered, p-n junction diode was known, only point contact transistor, but thereafter diffuse junction technology also came, and therefore this silicon p-n junction technology came automatically after the discovery of the fact that this material silicon can be very easily coated, not a painting type of coating or rather a deposition technique, simply by conversion of silicon into silicon dioxide. A very high quality oxide film can be grown on silicon by a very simple technique, and that film can be very easily patterned into the desired window pattern. This is called window pattern, and subsequently by a suitable doping technique. That time only doping technique which was known was diffusion, and of course epitaxy was also known, but ion implantation was not available that time. So what was the diffusion technology which was used in association with the oxidation and photolithography to form p-n junction, and by using this process repeatedly one could create various structures in silicon and certain techniques for isolating electrically these devices, that means transistors, diodes, resistors, capacitors, in certain cases inductors also. So after all, silicon is a semiconducting material. You cannot just place them, they are all electrically connected. So you have to do something so that they get electrically isolated, and that was possible. And that was the beginning, and that was the real start. Electronics, you know, entire electronics, and not only electronics, today as you see, all fields of engineering and every sphere of life have been changed. Today, as somebody was telling, we are telling about multimedia. You know, in USA what is happening? The children, the society is changing, and some people were very, very happy, particularly the industrialists or the businessmen, or some good thinker, they have started thinking about it. Is it good? Because the structure is changing. Too much use of multi. But it has all been possible because of one thing, starting with the discovery of transistor, and then gradually the rapid evolution in the field of IC technology, IC design, system integration. And today we are speaking of single chip systems. You know that the Pentium series, all 486, all innovative things which are coming today, they are mostly single chip based. A single chip, a single silicon chip of size maximum 2 cm by 2 cm, that's the usual limit, containing millions of transistors, MOSFETs today. Millions of MOSFETs, usually CMOS technology, and that is, creating havoc. Anything you can do, anything. It's a digital filter technique, otherwise digital filter research. Digital filter research was going on for a long time. Active filter research was going on but you know that an operational amplifier in those days, each operational amplifier was a small box. You just see the difference, what is the change today. And now, and that has been possible because of the rapid phenomenal progress in VLSI, ULSI. So our class, this particular subject deals with this VLSI, ULSI, an introduction to VLSI, ULSI, mostly circuit aspects and certain systems aspects will also be discussed or presented in this class. So before I go to the actual, today I think this is the first class, we will not go into the subject. I will give you some very starting introduction about the, firstly is the history. I already have told you about the starting. It starts with, but I will just note down some important, this is a very important record for you, that is why I have brought it. Let us note down. One is a bipolar transistor called BJT. It was developed in 1947, 48, as I told you, by Bell Lab people, and that was the starting point, so I will put a very, very important asterisk here. In fact, let me put a red line. It's a very important thing. Very, very important. And that was the starting. Next one is, in the line, junction FET. This device also came with a lot of potential, but unfortunately it was found that it was more important perhaps as a discrete component rather than as a component of IC. Then as I was telling you, the planar technology and planar transistor. This was of course point contact transistor. This one point contact galvanium transistor, first one. Then planar transistor. It came in 19, quite late. I should say not 59, I should say 58, not 59, 1958. MOSFET, which again revolutionized the modern ICs, in fact Vlsi, that came 1960. I have already told you some earlier during teaching device course that this MOSFET theoretically was known quite earlier. The principle of MOSFET theoretically was known quite even earlier than the bipolar junction transistor. But its practical implementation came later because of certain technological problems which were overcome, and therefore thereafter it. So in 1960 was the starting point of this thing. PCB in this modern form, printed circuit board, it came from Signal Corps, USA, in 1950. As I told you that photolithography technique was known earlier, but the art of photolithography as applied to microelectronics came later. It was given by Signal Corps for PCB fabrication. Then, as I told you, the concept of IC, theoretical concept of IC, it came from Dummer, D-U-M-M-E-R, of Royal Radar Establishment of UK in the year 1952. In fact, immediately after, within a few years after the discovery of transistor. Okay, concept of IC. He was a physicist basically, and of course he had a lot of engineering background. As I told you that US defense started funding the various organizations very heavily from mid-50s, realizing the importance of, as proposed by Dummer in 1952. Then it is a Jack Kilby of Texas Instruments, USA, who discovered the first IC. And that was, in fact, is something the history. Around the same time in 1959, which coincides with the discovery of the planar technology. Because it was the planar technology which was the main thing behind the development of first IC. And then, as you know, there was rapid progress. Op-amps came within a few years. In the digital gate area, TTL, still today one of the most important thing is in 1962 from the various labs. The MOS, I should say the MOS started with LSI. TTL was a medium scale or small scale integration circuit, whereas MOS started with LSI concept, and that is in 1962. You see, you have seen already noted that 1960 was the discovery, first practical realization of MOSFET. Within a very short time, the MOS LSI came in 1962. CMOS in 1963. MOS memory in 1968, again big step forward. Microprocessor, very important thing. This is actually, as all of you know, that the actual revolution in electronics, the overall engineering and the lifestyle of people started with the development of this 1971, that 4-bit chip. And as you know, thereafter I don't think it is necessary to write anything about history. You just go through the standard journals, you will find that since 70s, 71 to 80 was an era dominated by LSI, large scale integration. 80s onward, it became dominated by VLSI, whatever surface chips we are using today. And today's chips, they are calling it sub-micron integrated circuit, still called popularly VLSI, but the fabrication people, they call it ultra large scale integration, or ULSI. And another name is being very much sometimes being referred to instead of ULSI, that was not that much, the impact was less. They are called it RLSI, ridiculously large SI, R. So they have put that. Americans, as you know, that that way is quite humorous. So this name has been put by some American people recently. So that is the name to RLSI. As I told you that, the ICs today no longer is called VLSI, but the definition of this VLSI etc. already has been told, I think, I'm sure, by the teachers concerned earlier. It starts with device. Device means 2 to the power 0, or sometimes we say 10 to the power 0. 1. Then small scale integrated circuit, SSI. Start with that. This one will not do. SSI. The integration, I can say 10 to the power 1, so far as number of components are concerned, and 2 to the power 1, more or less, so far as number of gates are concerned. But let us put in the form of components. Medium scale integration. Per centimeter square. Not per centimeter square, per chip. So per chip. Large scale integration LSI 10 to the power 3. Very large scale integration 10 to the power 4. And there I will stop. I will not write any other things. You know that here, what I mean that small scale integration 10 means it is usually from 10 to 100. MSI 100 means 100 to 1000 roughly. LSI 1000 to 10,000. And VLSI really is above 10,000. In fact, in terms of components today, it is, you know that today it is not 10 to the power 4, it has really gone to 10 to the power 6 actually. You may call it VLSI and other things, but still the popular name is VLSI. So our course name, though it has been called in our syllabus, it is Integrated Circuits and Systems. It is perhaps a better terminology in today's, you know, if you want to create impact to the outside world, the better name is perhaps VLSI Circuits and Systems. This VLSI can be the classification, so far as the categorization or classification is concerned. VLSI can be classified in various ways. One is the form of kind of devices which is used. In that way, it can be called, VLSI has got two broad categories. One is called bipolar, the other is called MOS. This is one classification. Okay? Similarly, from another point of view, this is from device point of view. What kind of device is there? Other categorization, as you know, other categorization is analog, digital, and fourth one is mixed signal. This is very, very popular terminology today. And I think I should also add another term simultaneously from here, which I just forgot to mention. This is called BiMOS or BiCMOS. So from device point of view, what kind of devices are integrated? One is bipolar, called bipolar IC, MOS, MOS IC, and for MOS IC again there are classification. It started with PMOS, then NMOS IC, and it is all CMOS today. As you know, almost universally CMOS today for technological reasons. And then particularly when people are thinking of today mixed signal ICs, and very popular today, neither analog fully nor digital fully, but both analog and digital functions are performed on the same chip simultaneously, and that user today make use of normally BiCMOS process or BiMOS. It has been found that bipolars can function analog functions and do analog function a little bit more efficiently, and so far as driver is concerned, power capability concerned, bipolar is better than MOS. Whereas for performing all digital functions, memories and other applications, it is MOS which is almost unparalleled today. So people are now combining the bipolar and MOS concept in the same chips, and the circuits are called mixed signal circuits or also BiCMOS circuits. BiCMOS and mixed signal and BiCMOS, they can say they are interlinked. These two terminologies are interlinked. This is one thing. Similarly, we can also classify the circuits in terms of, you know, the speed and frequency. Speed. And when I speak of speed in digital language, in digital applications, what do you mean by that? Switching speed. Usually we define the speed, instead of writing speed we say propagation delay of a gate, single gate or overall system. But it is not the delay which is important. Simultaneously, another important thing is the total power consumption. So a product called power delay product is a figure of merit is a figure of unit of digitalizers. It is not only the power, but the delay, both are important. And as you know, nature does not give everything generously. If it gives one thing, then other thing will be a little bit miser. That way, an integrated circuit which has got higher speed would consume more power. Or if it consumes very less power, it will have a tendency to have higher delay. And therefore, you know that man is always, man is quite in nature's creation is man, and man is trying to compete with nature. Man's creation is computer, and computer is trying to compete with man, and that's what is happening today. So man did not, it is naturally, it is power delay product is a parameter. Man tried to optimize it by their brain power, discovery, innovativeness. So what they did, they went on discovering logic families, one after another, just to minimize this quantity. Started with TTL. As you know, it started with TTL, but before that, RTL, DTL, etc., they are not important. They faded away. TTL was excellent, but it was consuming a lot of power. Its delay was also not that short. They did something, man. The man, of course, I do not know, perhaps with God's help or nature's help, because ultimately it is brain, and we cannot create brain. So nature and God automatically comes in. If you believe in God, it is God, otherwise nature, it comes in. But you know that its term is STTL, Schottky clamp TTL. TTL has got a propagation delay of 10 nanosecond, but with Schottky they could go to even up to 3 nanosecond. It was possible. And thereafter, there are a series of things in bipolar technology. You know, a very, very high speed thing is there. It is called ECL, emitter coupled logic. Its propagation delay usually around 1 nanosecond. Unfortunately, again, it draws a lot of power. We shall know about it, and we shall also discuss it a little bit afterward. But we know about it, what is the advantage of ECL. And then came PMOS. Its power was less, but this thing was worse, around 20 nanosecond. Okay? And starting from that PMOS, technologically it was convenient, that was why it came first, which is around 20 nanosecond. Power consumption was less. Then came NMOS. Its power consumption could be reduced to the range of 10 nanosecond, but its delay could be reduced to the level of 10 nanosecond, but power consumption was still higher, on the higher side, tens of milliwatt. And then came CMOS, from hundreds of milliwatt to around a milliwatt to microwatt range. But again, the delay was initially more, 20 to 30 nanosecond, very low power, could be 100 microwatt to a milliwatt first. In that day, when it first came, but there was a lot of innovation lot of technological advances. And now present CMOS, modern CMOS, comes with a delay less than 1 nanosecond, 100, 200 picosecond, power less than even times 10 microwatt. And you just see now the picture where if you find out the power delay kind of things, have you know perhaps this picture? If you have this side power and this side delay, okay, if you are in the for TTLs, we are somewhere here. For TTL, for CMOS, we are somewhere here, and it is going towards the origin. And for ECL, we are somewhere here. Our tendency must be to go towards the origin. That means a region where power is almost zero and delay is almost zero. Can you tell me, any one of you, that which one has got the most promising thing for going there today? Yeah, CMOS, low temperature, and you know that innovative structures, just not only ordinary CMOS, but various innovative things with incorporation of heterostructure modulation of FET, HEMT, as well as Josephson junction devices, and all the, unless you then supercomputer, the future supercomputer have to use. But CMOS only thing is by technological innovation, making size small and all this, fabrication and some device analysis point of view, they have been able to go to around 100 picoseconds today, and the power consumptions around a few microwatts, and that's possible. But people are thinking of picoseconds, nanowatts, simultaneously. So man has not stopped. Its brain is there. It's going ahead with that, and future people perhaps will see that ICs are coming in three-dimensional form with very, very high packing density, just like our brain, and speed power point of view, it is far, far superior to that in brain. Already it is far superior. But so far as packing density is concerned, we are very inferior.